Okay. All right, today I want to do a quick recap of some of the properties we talked about yesterday. Now, I'm not going to allow you, I know some of you were gone, like Taylor, I know you were gone and stuff. I'm not going to allow enough time for you to write down everything we're going to do here for just this recap. I just want to review the properties that we talked yesterday. So we had Theorem 4.5, that was a new one yesterday. That was one of the new acronyms, right? We had the 3-letter acronyms, that was one of the new ones. And we also went 4.6 to 4.9 yesterday in class. I want to review those properties one more time, okay? Now remember, before we get to 4.6 and 4.9, there were some vocab words that I'm going to go over one more time, so that way you know. Now, the goal, why I'm reviewing these today, is because my goal was to give you some pictures of different geometry problems that I saw in your book, and all I want you to do is just look at the picture and tell me, are the two triangles equal? That's all I want you to do. It's a yes/no question. Are they equal or not? Once we get the flow of that, I want to know like the reason. And so we'll go back and we'll look at the reasons. And we'll look at, okay, is it by, LL theorem, or is it by HL theorem, or HA theorem, or is it by, angle, side, that sort of thing. We'll talk about, there's different ways to actually prove things. And that's what these new ones are, okay? So real quick, and so the idea was to go through a couple examples of like applying those theorems to these things. To tell me yes or no, are the triangles equal. We'll do a couple rounds where I think I picked out two where we're going to find a missing value on a picture, like find X on a picture that I'm going to give you. And then one of the other questions that I had picked out, I don't know if we'll get to them today, is to do two proofs. Two proofs of like applying the new stuff. So like, are these things equal? Do you know why? That sort of thing. Okay? Make sense? Okay. So that's what we're going to go to today. So I'm going to go through this pretty quick. You won't have enough time to write these down. I'll have it on the website tonight when I update it. I don't think I updated yesterday, so I need to make sure I do that sometime this morning. I'll post the video and stuff today. All right. This is one of the ones we had yesterday. You're given two angles and a wall that is not in between them. Two angles and a wall not in between. So here's the picture. Right? So you're given two angles and a wall not in between. Well, that's the setup on both pictures. The triangles are equal because of the new acronym we have is called angle, side, AAS. It's one of the four that we should have. Okay, it's the last of the 3-letter acronyms. Right? We had SSS, SAS, ASA, and then this one. This is the new fourth one. Now, the reason why this one works, we talked about yesterday, was you could find the third angle using the third angle theorem. That two angles were given, so the third one has to be the same, and then it would be by ASA. So we proved it using other postulates we've had. So it is a quick proof. I think it was a 3-line proof we talked about yesterday. But anyways, according to this theorem, these triangles are equal. So I think it's going to be like one of the pictures we do today. We'll actually use this. Okay. But again, are these triangles a right triangle? No, they don't have to be. Remember, the 3-letter acronym system, SSS, SAS, ASA, or this one, AAS, they work on any type of triangle as long as the setup's correct. The pictures have the right markings in the right order. That's why these are kind of cool. Okay, so that was a new one we did yesterday. Now, we did some vocab before we got into our brand new stuff yesterday. We talked about a leg and a hypotenuse of a right triangle, because we were dealing with right triangles at the second half yesterday. Right triangles are a triangle that have a right angle in them. Right? So there is a right angle in that picture. Now, the legs here, there is plural. The legs are the two walls that touch the 90, and the hypotenuse is always the longest wall. Okay? So that's something we talked about yesterday. Now, we also talked about that when you look at a right triangle, there's two classifications you can call it. Right? You can call it obviously a right triangle, but you could call them scalene, or they could be isosceles. That's it. They cannot be equilateral or anything like that. Because right triangles, according to like this picture, these 3 walls are different. So the 2 legs are different sizes. So it's scalene. Scalene is when all 3 walls are different. Now it could be an isosceles picture. I should have added it to the slide. Maybe I'll do that tonight before I post it. But isosceles right triangles are when they have the 2 legs are the same size. The hypotenuse is still the longest wall. But that would be an isosceles right triangle. But those are your only 2 options you could call it. So keep that in mind. Now, the word isosceles is something we're going to probably start looking at maybe as early as tomorrow, because we still have to prove the last theorem that we did yesterday. Okay, now the theorems we talked about, we added, we had, I think it was 4. It was 4, 6, 4, 7, 4, 8, 4, 9. They are only dealing with these pictures. Like, if you looked at a right triangle, would you know that they're instantly equal to each other? And so we had a bunch of different acronyms that we could use. Now, they still fall back on, SSS, SAS, ASA, or AAS, but this, the ones we did yesterday, 4, 6 through 4, 9, they were just like quick shortcuts. Like, if you looked at the picture, yes, they're equal because of this. You didn't have to do a full-on proof, but today we're going to look at that, okay? But these are the vocabularies we talked about. Now, the 4 theorems we talked about, 4, 6, this is where you're given the 2 legs were equal on a right triangle. These are the legs, right? The legs are the 2 walls that touch the 90-degree marker. We talked about that, the hypotenuse is the big wall. So they're giving me the 2 legs are equal from one triangle to the other. And so what we said is, according to this theorem, they are equal. Because the reason why was this reason. That the side, angle, and side markers were given to you so that the triangles are equal, because it does spell one of the 4 acronyms we have. Now the reason, the name of this one is called the leg congruence theorem, right? Leg congruence, I should say, LL theorem, that's what we called it yesterday, because the legs were given to you, okay? But yeah, so again, these only apply to right triangles though. Okay, then the other one we talked about was 4, 7. You're given the hypotenuse, the longest wall, and then a random angle, one of the acute angles, so a hypotenuse and an acute angle. These triangles are equal because of this last one, AAS, angle, side. The wall is not in between, so it's angle, side. But again, this is called the HA theorem, or hypotenuse angle congruence theorem. I called it HA. So that's what we talked about yesterday. 4, 8, you're given a leg and acute angle. A leg and acute, and it didn't matter which ones you were given, just one leg, one acute angle. These are the 2 acutes, they're the small angles. But as long as you're given those 2 markers on a right triangle, that they're automatically equal. Now, we used this picture yesterday, and I said I didn't like this picture. But anyways, it was, the reason why this one works is because of angle, side angle. That was the reason why this one worked. You can actually see the markers. Okay, and now the name of this one is called the leg angle theorem. The last one we did yesterday, and we did not prove this one yet, it was 4, 9. This is called the hypotenuse leg theorem, right? You're given the hypotenuse, and you're given one of the legs are marked, and that forced the 2 triangles to be the same. Now we talked about yesterday, this is the inappropriate acronym when you look at the markers themselves, but we haven't proved this one yet. We haven't talked about like why this one works, other than it just does for right now. We need the next section to be able to prove it. We need one property before I come back to this. So I said that, possibly tomorrow or today or tomorrow we're going to get to it. It's probably tomorrow if we can get to section 4, 6. Okay, questions. Okay, that's a quick, 2-minute review of what we did yesterday. That was quite a bit of stuff. So again, watch the video, get those PowerPoint slides, or write down some notes from yesterday, whatever you had. Okay, so definitely do that. I'll try to update the website today. Okay? Okay, questions, comments? Perfect. Okay. Homework that we had yesterday, if you did not, if you were not here like Taylor and stuff, that is due today now. That was page 268 and the 278. You needed a graph. I know some people forgot to turn that in yesterday, or you were going to turn in later in the day. If you did not turn in, you need to get that in, because I'm going to get those in the grade book, and you'll need to have those scores in. Okay? Start of the second semester, we need to have those in. Okay? All right. Now, let's get rid of that. Hopefully that was enough review for you. The goal today is do a quick run through some examples. So I'm going to put this up here on the board. Hopefully this works. We're gonna talk about, with these 2 pictures, are the 2 triangles equal? That's what I want to know. Okay, it's a yes/no question. And then once we get through into yes or no's, we'll try to get a group consensus. We're gonna go back, and we're gonna take a look at how do you know? Like, what would the reasons be? Because each picture will have it possibly 2 different reasons why these could be equal, which is kind of a nice thing, that you have 2 reasons that back your information up. Okay? Okay, so let's talk about this first one. two triangles, they have the markers on them. Yes or no, are they equal?
Yes.
Yes, okay. So we're saying yes. That seems like the group consensus. We don't have any, I didn't hear any no's anyway. All right, I agree with you. It is yes, they are equal. Now, there's two reasons why. What's one of them?
Both of the legs are equal.
Both legs. So it is a right triangle. So according to the right triangle properties we had yesterday, it was by the LL theorem. Right? That is one major reason. Leg-leg theorem. Another reason.
They're both 90 degrees.
Okay? Both 90-degree triangles. Okay? They both have angles in them. Okay? So that, how could that help me? Because you're onto something here. They are 90 degrees. What else?
Yes.
Yeah, that would be the other reason. Like having your 90 degrees and having these legs being equal, it could also force this to be by SAS. Side, angle, side. So there is two reasons why these triangles are equal. Again, number one, LL theorem because of the 90-degree angle. But then the second reason, this is like one of our main acronyms we've had the last couple of days. That's another reason why they're equal. The markers spell the right acronym and they're in the right order. Okay? All right, makes sense like what we're doing here? Okay, all right. Let's go to another picture. I just have a bunch of these. I think I have like 4 or 5 of them. Okay, next one. All right. So we have the markers on the picture. Yes or no, we'll just get a group consensus. Raise your hand if you think yes. Okay, 1, 2, 3. Okay, we're over half. All right, so we'll say yes, group consensus. Okay, so we're going to say yes. There was a couple of people that didn't raise hands. I think they were just kind of trying to figure out if it's a yes or no. Okay, so other than my first 2 people that volunteered, somebody that said yes. Morgan, what do you got?
ASA.
Say it again.
ASA.
Okay, that would be a main reason. ASA. That is one of our 3-letter acronyms that does spell why these are equal. So this is most definitely a yes. I agree with that. That's a resounding yes because that's one of our first postulates we have. Now, is there another reason?
The acute and the leg.
Yeah, it's called the LA theorem, the leg angle theorem. Okay, I call it the LA theorem. I don't really care about the numbers, but anyways, this particular theorem only dealt with right triangles, which this is a right triangle. They do have the right angles in them, so they do have 90-degree angles. But this was another reason why it worked. They gave you a leg, and they gave you one of the acute angles. But like Morgan said earlier, like one of the main reasons is because of that postulate we had earlier, angle, side angle. Okay, but I do agree, there's 2 reasons why this thing works. Okay, questions about that? Now notice, I didn't put the theorem number. I didn't say this is theorem 6.8, which I think it is. I just care that you know that it was a leg angle. Like they gave you a leg, they gave you one of the angles, and they are in the correct order. The big thing is actually looking at the picture and seeing the markers are in the right, in the right spots. Like from this picture to that picture, if the markers are in different locations, it may not be equal. Okay, that's good so far. So far, so good. Let's keep going. So now on this one, you're looking at like, well, they only have 2 markers. Ah, okay, so they're the reflexive wall. So we can put a marker here. They do have the reflexive wall. They do share a wall in the middle, so we can make that mark. Yes or no, what do we think? Are they equal or not?
Yes.
Okay, we had a couple of yeses. Anyone say no? Okay, I agree. It is a yes. Now, on this one, there is only one reason.
Side, angle, side.
Nope. It's not it. It's not side angle side. It kind of looks like it when you like loop around. It looks like it's going side angle and then another side, but the angle's not in between them. Like if this angle marker was here, then yeah, it would be side angle side. We don't have an SSA theorem. Yeah, we don't have an SSA. That's the inappropriate one, right?
LA theorem?
Yeah, it's not LA theorem, not leg angle theorem. It's not that one because LA theorem requires an acute angle, not the right angle. By the HL theorem, hypotenuse leg. The hypotenuse is actually the reflexive wall. They are right triangles. They gave me the hypotenuse in the middle, and they gave me one of the legs. That's actually why they're equal. This is actually the last theorem that we haven't proved yet. Now, the bad part is, and I even heard it earlier, doing the acronym here, side, angle, right? We don't have that as one of our four. One of the four acronyms we have were these. These are our four acronyms, right? It kind of looks like this one, but it's not, because the angle's not in between the two walls. But it looks like these, but that one spells the inappropriate one, right? The only reason we have as of this moment why this works is because of this. That was the last theorem, 6.9, HL
Prove
theorem.
that one
Yeah, we haven't proved it yet. But that's the only reason why this thing works so far. We need to talk about that one tomorrow, though. Hopefully we get to it tomorrow, that we can prove why it works. And we can figure out which acronym actually does justify it. But it does take a pretty serious proof to do that. Okay? Alright, but yeah, so that was kind of a tricky one. That was probably one of the harder ones I saw in the textbook. Again, I pulled all these problems from your textbook, and I was just trying to see, I took all the words out, I just want to see if you guys can figure it out. Okay? I think this is one of the last ones that we have. Okay? I think it's one of the last. I don't think I have another one. No, I have one more. There's one more after this. Okay. Yes or no, are they equal? Yes. Okay. We're saying yes. Now why? Say it again. LA theorem. Okay, I agree with that. LA theorem. Okay, leg angle theorem. That is a leg. That is a random acute angle. So that does work. They are right triangles. So that is one of the reasons, because again, they are right triangles. So that's why you can use the LA theorem. And what was another reason? What acronym does it spell?
ASA.
ASA, yeah. ASA theorem. Or postulate, I should say. So that would be another major reason why these things work. But LA theorem is probably the first one. Since they are right, you can use that. So there's always two reasons. Okay? I think I have one more picture. Let's see. Yeah, I had that one. One more. I think this is the last one. Okay, what do you think? Yes, no? Okay, a couple people say yeah. Okay. You want to say no? Okay, we have one no. Two no's? Okay, let's talk about the yeses. What acronym would it spell, or what theorem do we have, like an HL or something like that? Are they marked? So somebody give me a reason that we're saying yes. Any reasons? Or maybe if I don't want to put you on the spot, maybe something that said no, what would be a reason?
There's no sides that are the same.
Yeah, there's no sides that are the same. In fact, we can't prove this one. They could be, and don't get me wrong, they could be the same picture. It doesn't look like it, but they could be. Right now, we can't prove it. The reason why, you're absolutely right, there is no wall marker whatsoever. No walls are marked. In fact, if we were just put the little acronyms in here with the little letters, all we have is angles. All we have is angles. A. We don't have an A acronym. In fact, the only thing I can really tell you as of this moment with this picture is, since all three angles are equal, I can tell you that they could be quote unquote similar to each other. Now, if you've never heard the word similar, I've talked about it a little bit before. Similar means they could be close to the same picture, but the main word here is that they're actually proportional. What I mean by proportional, they're scales of each other. It's like the idea of if you had a real car versus a little toy model car. The real car and the model car are identical in proportion. Maybe the model car looks like the real car, but it's not the same value, right? The sizes are off. It's like when you have a toy tractor versus the real tractor, they have a scale there. It's at 1/16th or it's 1/64, the size. They look like the same, everything. The wheels are in the same proportions. They're actually similar, but they're not equal to each other. The values aren't. They're different sizes. That's what's happening here. these walls could be the exact same size as they could be, or this wall, like all the walls could be just shrunken down just a little bit. Maybe each wall is 80% as long as the original wall. So if you took this wall and took it times 80%, like 80%, shrink them all down, maybe that could be this picture. They'd all be the same scale to it. But don't get me wrong, it could be equal, but I can't prove it, because only the angles are given. That's something we're going to go into. Like, how do you know? Like, how do you know that they're the same? Or are they close? This is something we're going to get into later, this idea of similar, or similarity. Okay, hopefully that got us in the swing of things. You're starting to think about, like, there's multiple reasons why triangles can be equal. We're starting to get to multiple properties now. Okay, so you don't have to waste so much time in a proof. You can use different reasoning to do it. Okay, now, I did have more. Okay, I didn't realize I did. That's hypotenuse, angle. I didn't realize I had 6. I didn't realize I picked that many. All right, anyway, let's get to this one. So this is one of the problems that I picked out of your book that I thought it was interesting enough. The question that they asked for is find the value of x, according to the picture, that makes the triangles equal. So I want to make, this triangle BCD equal to WXY. I want to make the triangles equal, and I want to find the value of x that can possibly do that. Okay, now there's 2 ways to do this problem. 2 ways to do it. Number 1, you can use the walls to help you out, or you can use the angles. I don't know how you want to do it. You guys want to use walls or angles? How do you want to do it? Which one looks easier to you, walls or angles? Angles. Okay, well, let's go with an angle. So what I would probably do is I would probably try to find one of the angles here, so like angle B. So I'm just going to pick that one just for instance, because this thing is sitting in right in angle B spot. This thing goes here. Okay, so that's the 24x plus 5. That angle, according to the label up here, is supposed to be equal to this angle, letter for letter. So angle B is supposed to be equal to the first letter over here, because they're the first letters match. So it's supposed to be marked with a W. So this should be the same angle according to that drawing. So it looks like what it looks like they did is they took this picture and like flipped it over like a pancake. Over there. And we need to solve for x and see if the x actually makes this whole thing work. So, and what we'll do is once we have x, we'll plug it in and see if it actually does work. We'll plug it into like that x over here, and we'll see if it gives me the 11, because I think the 11 is supposed to be that wall. Now the BC wall here, that's the first 2 letters, that's supposed to be equal to WX, that wall. So we're going to actually see if it does work. Okay, they could be positive, they could be negative numbers, but we do need to check this. So 24x plus 5, that's supposed to be equal to the 77 over there. So I'm going to subtract the 5 across. So that's 72. Divide by 24. Divide by 24, what is that, 3? Is that 3? Okay. So that's my x, and now what I want to do is I want to check, does that work? Now I don't care about plugging the 3 in here, because I don't really even care what that angle is, there's no angle to mark over there. But I do want to check if the walls work. So let's take this 3 and let's plug it in right here. So 2 times 3 plus 5, what is that, 6 plus 5, which is 11, and yes, it does give me the right number. So yeah, so 3 is the magical number. This is the magical number that I need. It does make the triangles equal, and then I can get to all the reasoning. Okay, questions at all with what we did there? Okay, now if I had to prove that these triangles are equal, I don't think I'd have enough information. I could, potentially. I could plug the 3 in here, figure out that angle, figure out this angle, which is, this one's 77, by the way. But I could plug in the 3 here, and then I could find this missing angle, and I could see, are the triangles, maybe it's a right triangle. I have no idea, but maybe it is. So then I could figure out, are the triangles actually in fact equal to each other? I could justify reasoning. But I think the only question is find the number for x that makes it work. So sometimes they give you extra information you wouldn't need, like this little piece. Right now I don't need it. Unless they ask me to justify it. Okay, let's do another one. So, same question. I want you to find the value of y that makes these triangles potentially equal to each other. Find the value of y that would make these angles equal to each other. This one's actually kind of challenging. It's kind of tough. When I first looked at it, I was like, okay, that makes sense, but there's like two ways to attempt this, but to justify, to see if it actually works, that's kind of the tough part. But I'll give you a little minute here, just to kind of fill you on. This is the angle down here in the corner. This angle is actually here. The 53 sits here. This 2y minus 1 is this wall from like J to Q. And then this wall is 9, and that wall is 8.1. So I'll give you a little bit of time to see if you can figure that out. Again, you want to solve for y.
So vertical is equal.
That's actually something we'll talk about too. Yeah, it's probably our last problem of the day, but. Yeah, give me another minute or so here. And it said there's two ways you could potentially do this. One is more tricky than the other. All right, I'd like to know somebody's opinion. How did you attempt this problem? How do we do it? How did you attempt to find y? What was your strategy? So there was two ways. Okay, Nelson, what do you got?
Well, the 53 would go to the other angle.
Okay.
So the 13y, the 14y minus 8, and the 53 would equal 180.
Okay, that is probably the more difficult way. I agree with that. She transferred the 53 across. What property is that called?
Vertical.
Vertical. Okay, good. Heard it. All right, so vertical, and then she added up all the angles to make 180. Because remember, triangles have to add up to be 180. That is by far probably the more difficult way of doing it. Don't get me wrong, it does work. It is true that you can do this. Get 180, right? You can add up all three angles together now to make 180. So you'd add the y's together. That's 27y. Subtracting the 8 here, what is that? 45 equals the 180. You could add the 45 across and get 225 or something like that. And then divide by 27. I have no idea what that is. Say it again? 5? Okay. Oh, okay, so 5. Now, there's another way to do it.
Did you subtract the 45 over? Or add the 45?
Oh, what am I doing? Rookie mistake. What am I doing? Let's see. 40. Okay. 135, then divide. Yes. What is 135 divided? Is that 5s?
Yeah.
Okay, I'm a dork. Just ignore it. All right. But anyways, what's the other way to do that problem?
So 2y minus 1 equal to 9?
Yeah, exactly. That would have been the other way. Now, because most people wouldn't see that, like you wouldn't think that those are equal. The reason why you would need to know that, like J to H is that one. J to Q is this one. Those walls should be the same because the letters land in the same spots. So the back two letters should equal the back two letters over here. So that means the walls should be equal. So that's why you'd set these equal to each other. And then you'd add the one across, but I'm actually doing that right for once, and then you would divide by 2, and yeah, your J would be 5. Or, J, what am I doing? Good Lord. That's a Y, so just go sit down. Alright, so Y should be a 5. So there's two ways to do it. Now obviously one is easier than the other, but they did give you the same number. So, Although that does make sense, okay? And then you could actually take all the numbers and plug it in. So I could actually find a couple y's, or a couple of different numbers. I could plug the, the 5 in here, find that angle, find this angle, transfer those over. I could take the 8.1, transfer it over here, and you could see what all the walls are. I wouldn't have one wall, basically. All right, questions, comments? Perfect. Okay, done for the day, all the good stuff. We'll get to the proofs and stuff tomorrow, because I still need to prove, 6.9. We haven't proved it yet.
4.9?
6.9?
4.
4.9. I should just say that. I'm in a different world today, I guess.
You said that earlier today, you said 6.9. I was like, we already did.
Ah, no. I didn't even catch it.